All right, so this is lesson 20.3.4. It's the fourth topic, dealing with circular motion and applying it to Newton's laws of motion. This is on page 14 of your unit handout. We're dealing here with vertical circular motion, and this is a very slippery kind of application. As a warm-up, we're going to look at a 500-gram ball. It doesn't really matter what mass we use, but I chose a mass here. We've got a 500-gram ball. It's attached to a 1-meter-long string, and it's swung in a vertical circle at a constant speed. So I want to make sure you understand what this means. It means that as I'm standing here twirling the ball around and around, there is a point in time where the ball is above me, and there is a point in time where it is almost on the ground. If this is the ground, what we're talking about doing is twirling something in a circle. I guess I can draw the ground as a straight line. We're talking about twirling something in a circle vertically. So at some point during this object's orbit, it is close to the ground. At some point, it is above that point. So it's a vertical circle. We're not talking about driving around a curve. What we're talking about is going in a vertical circle. So the first question is asking us to explain, well, first of all, when you do this, and it doesn't matter whether it's a vertical circle or not, you're going to have to pull on the string to get the object to move in that circle. If it is a vertical circle, the question is, why does the applied force at the top of the path, why can it be less, and why is it less than the applied force at the bottom of the path? And if it's not intuitively clear to you, you might want to try finding something that you can attach to a rope and twirl it around in a vertical circle. And you will discover that when the object is at the bottom and you are trying to pull it up to keep it in its path, you have to exert more force than when it's at the top and you have to pull it down. So does anybody have an idea as to why that's the case? Why is it that when it's at the top, you don't need to apply as great of a force? So there's a gravitational influence, perfect. And we want to be a little more specific. The idea here is that when it's on the top, yeah, that's a nice addition to it. When it's at the top, gravity is working with you. When the object is at the top, you're trying to swing it towards the bottom, but gravity is helping out. When it's at the bottom, you're trying to pull it up back into the curve, and gravity is resisting your efforts. So what we can say is at the top, the force due to gravity helps curve the ball because it's curving it towards the bottom, but at the bottom, the force due to gravity resists your efforts. And maybe, you know, we're going to end up coming to this conclusion at the end of this lesson, but maybe that's where you have to start here, is you have to understand that the applied force at the top is going to be less. Okay, compare the centripetal force on the ball when it is at the top to when it is at the bottom. So what I would like everybody to do is give some thought here, and I don't want you to type any responses just yet. I want everybody to give some thought as to how the centripetal force experienced by the ball at the top compares to the centripetal force experienced at the bottom. So I guess what I'm asking now is the following. We're not going to worry about the direction here because, of course, the centripetal force changes direction. What mathematical symbol could I put between these two that would create a true statement? And now I'm going to ask you to type your answers. And if you don't quite get my drift, there are a list of mathematical symbols. We could say greater than. We could say less than, or we could say equal to. So the question is, which of those mathematical symbols do you put in between there? Is the centripetal force at the bottom greater than the centripetal force at the top? Is it less? Or is it equal? Wow, Farhan and Ben and Sienna come from behind and win it. And Andrea, they are equal. Why are they equal? Well, what is centripetal force? Centripetal force is net force. And the net force is mass times the acceleration. But the acceleration is v squared over r. The force is the net force. It's the same everywhere. The speed, and this is why I bolded this, the speed is a constant speed. What's changing is the amount of force you need to apply to make it happen. At the bottom, the applied force is greater than the applied force at the top. But at the top or the bottom or in between, the centripetal force is the same everywhere. Okay, on the diagram, draw all of the forces acting on the ball. So here's where now we really get into the sticky stuff. If I draw the force of gravity acting on the ball when it's at the bottom, I will have to draw the exact same force acting on the ball when it's at the top. So when you draw these two forces of gravity, they need to be equal in magnitude. Because the ball's mass hasn't changed when it went from the bottom to the top. So this is the force due to gravity. This is the force due to gravity. Are there any other forces? Well, yes. There is another force acting on the ball when it's at the bottom. And that other force is the applied force by your hand. You are applying a force upwards. And I'm just going to offset this so you can see the string. There is an applied force upwards here. F applied. And over on the other diagram, there is an applied force, but this time the applied force is downward. When you're swinging this around, you are always pulling the object towards the center. So what we have is the applied force downward here. Are there any other forces acting on the ball? I'd like everybody to think about that. We're into highly conceptual ideas here. Are there any other forces acting on the ball other than the force of gravity and the force that you were applying to the ball by pulling on the string. Now that everybody has had time to think of it, I just want to know yes or no here. Andrea and Liam say yes because they say there's another force called the centripetal force. I want input from everybody here. Is there another force acting on the ball? Yes or no? Okay, Liam changed to a no, but Ben says yes. Don't give me any reasons, please. Mackenzie says no. I don't want to know any reasons. I just want to know what you think. Tyson says no. Oh, the tables are turning here. Sienna says no. What if everybody's just getting on the no bandwagon and the answer is actually yes? Another no. Well, I will end the suspense. The answer is no. There are no other forces. And the reason is, and what Andrea said initially, which was the centripetal force, question mark, is what everybody thinks initially. The centripetal force is not an extra force. The centripetal force is the net force. So the centripetal force is the sum of these forces. It's not another force. It's the result of everything added together. So that's it. Those are the only forces. The next question says, what is the relationship between the applied force, the force due to friction, and the centripetal force? Well, don't forget, centripetal force is net force. So the relationship is, and what I'm about to write is true whether the ball is at the top or the bottom. The net force, which is the centripetal force, will always be equal to, for vertical circular motion, the gravitational force and the applied force added together. I want to be very careful here. I'm not talking about magnitudes, I'm talking about forces here. You have to add forces together to get net force. Net means total. So you add the forces together. But if I look now, and I would like you to look at the screen now, if I look at my diagrams, when I add those two forces together when the ball is at the bottom, I'm going to add them in a certain way. I'm actually going to take the applied force and subtract the force of gravity to get the net force in terms of magnitudes. If I add the forces on the right-hand diagram, since they're in the same direction, I'm simply going to add the forces. I'm going to add the magnitudes. So now let's take a look at the next question. Find the applied force when the ball is at the top. Well, let's do some calculations here. Let's calculate the force of gravity, everybody. I want everybody to take a second and find the magnitude of the force of gravity acting on the ball. So you're going to have to take the mass of the ball times 9.81. And I believe you're going to get 4.905 newtons. This is just mg. And that would be the force of gravity acting on the ball when it's at the bottom. Let's calculate the net force. So how do we calculate the net force? We go m times a. What is another thing I could call the net force? I could call it the centripetal force, but I'm choosing net. How do we calculate the acceleration for an object moving in a circle? It's v squared over r. So the net force will be mv squared over r. I would like everybody to take m, which is 0.5, times v squared. Do we know v? I'm just going to check here. Yep, 4. So you're going to take the mass times 4 squared divided by r, and I believe you're going to get 8 newtons, but I don't know. I just did that in my head very quickly. Can I get somebody else to verify? Evan did, Liam did. Mackenzie, Faran, Andrea. Okay, we're good. 8 newtons. Now, I'm going to go back to my diagram just so that, I mean, your diagram's right in front of you. You don't need to flip around. But that means over here, everybody, if you take a look at this diagram, the net force when it's at the bottom will have a magnitude equal to the magnitude of the applied force minus the magnitude of the force due to gravity. When you look at the diagram, when it's at the top, the magnitude of the net force will be equal to the magnitude of the applied force plus the magnitude of the force due to gravity. Because when it's at the bottom, those two forces are opposite, so we have to subtract them to get the net force. Now, what does that mean? It means, so I'm answering the next question here because the diagrams are right in front of me. What it means is that the net force that we got of 8 newtons is equal to the applied force minus the 4.905 newtons. So we add 4.905 to both sides and get the applied force is equal to 12.905 newtons. How is my arithmetic, my adding of those numbers? All right, on the right-hand side, we have F net, which is 8 newtons, still 8 newtons, equals the applied force plus the force due to gravity, which is 4.905 newtons. So that means when I subtract, I get a magnitude of the applied force equal to 3. I need some help, 095? Okay. Now, I want you to notice we've come full circle. Get it? Full circle? We've come full circle here because we said that the applied force at the bottom has to be more than the applied force at the top. Because at the bottom you're pulling against gravity, and that's what ended up happening. We ended up with more force at the bottom. All right. So we've calculated the answers to 6, or 5. For 6, when it's at the top, the net force has a magnitude equal to the applied force minus the force of gravity, which means the applied force, when it's at the top, sorry, this is plus. Question 6a refers to the diagram on the right. When it's at the top, you take the net force, which is mv squared over r, minus the force due to gravity. When it's at the bottom, when you look at the diagram on the left, which is where it's at the bottom, F net equals the applied force magnitude minus the force due to gravity's magnitude, which means the applied force when it's at the bottom is equal to the net force plus the force due to gravity. And I guess You know, maybe to summarize this a little bit, and this lesson is going to go pretty much till 11 o'clock. So you're going to have homework outside of the official 2-hour class. I guess we can put these two together and say the following, that the applied force will always have a magnitude equal to mv squared over r plus or minus mg, depending on whether it's at the top or the bottom. If it's at the top, and this is where some common sense comes in, if it's at the top, then you're going to subtract the two because you should know that the applied force at the top is less. And what I'm going to do throughout our work on this kind of stuff is simply say that over here it's mv squared over r minus mg when it's at the top, and here it's mv squared over r plus mg when it's at the bottom. Because I know at the bottom I have to work harder. All of that is a warm-up. All of that we spent as much time as we did on it so that when we do the examples, it becomes very, very simple. One last thing we have to do, which is number 7, is, do you agree that if you didn't swing the ball fast enough, it wouldn't make it through the top? So the question is, how fast does it have to move? And that speed that we're after is when the applied force just equals 0. As long as there is a little tiny, tiny, tiny applied force, then the ball is going to make it down. And you know what we're really saying here? Is that the slowest speed possible is going to be the speed where when it gets to the top, you don't have to pull at all, which means when it gets to the top, gravity is doing everything for you. And what that means is the net force at the top is just the force of gravity. You do not require any additional effort. Now the net force, we're going to do this so many times, the net force is ma, this is mg. However, the acceleration is centripetal, so this is really mv squared over r. We can actually cancel the masses here to solve this problem. V squared over r equals g, which means the minimum speed will be the square root of rg. So this is going to be the square root of 1 meter times 9.81 meters per second squared. I need somebody to let me know what you get for the first decimal place of this answer. 3.1. Thank you, you guys. So if you tried to swing it around at 3.0 meters per second, it would not be successful. A little note here, because we might encounter this. Very often, rather than saying applied force, we use the word tension. That's nothing new to you, I hope. The applied force can be thought of as the normal force if you have an actual path that the object is on, an actual surface. So if you've ever, as a child, played with Hot Wheels, you can get little cars going through vertical circular tracks if they're moving fast enough. And the normal force, also known as the applied force, also known as the apparent weight, those are all the same things. So the apparent weight is the normal force, which is the applied force. So as we go through some of these questions, you might see this, you might see this, or you might see normal force. They're all applied force. Evel Knievel was a stunt person in the 60s, 70s, and 80s. Jumped motorcycles across canyons, all kinds of stuff. So number one, a pail is swung in a vertical circle of a radius 0.8 meters with a speed of 4 meters per second. What's the tension at the top? So here's where I cut to the chase, everybody. All that warm-up stuff, I don't want to have to do that every time we do a question like this. The tension at the top, the applied force at the top, is going to be mv squared over r minus the force of gravity, because at the top gravity helps out. That's what you need to kind of remember here. So this will be 6 times 4 squared divided by 0.8 minus 6 times 9.81. I'll give you a few seconds to calculate what we get here. Again, I'm leaving out the units because you know to put them in on an exam or an assignment. I'm leaving out the derivation of the formula because, my goodness, how many times do we have to derive that idea? So let me know what you get when you've got an answer, please. Looking like 61.4. So I'm going to have faith in my class that yes, indeed it is 61.4 newtons. What do we do in B? Well, in B, it's at the bottom. And when it's at the bottom, more force is required. So in question B, we simply change our equation. If I can get that off of there. There we go. We simply change our equation to mv squared over r plus mg. I just want to check. Was it 61.14? Did I write 61.4? Is that what the... Oh, yeah, okay. Thank you, Andrea. This is actually 61.14, so I'll just call it 61.1. And while I'm fixing my mistake, thank you, Leslie, I want everybody to calculate what we're going to get for the tension at the bottom. Getting 179 newtons. Again, everybody, I don't think these things are things you want to calculate in steps. I don't know when it happened, and you don't know when it happened, but we've gone from putting numbers in to separate formulas to building a single formula that we can put all the numbers into. We didn't calculate mv squared over r. We didn't calculate mg. We're calculating mv squared over r plus mg. Can I get a couple more people to verify that it's 179 newtons? Okay, good. And the third question is, what's the minimum speed required? Well, the minimum speed happens at the top, and it happens when the applied force is 0. And if the applied force is 0, then the net force is only being provided by the gravitational force. And that means that mv squared over r, which is ma, equals mg. This is the same as question 7 in our warm-up. The masses cancel. If I cross multiply, I get v squared equals rg. So v equals root rg. We're going to take the radius of 0.8. And multiply by 9.81. And then take the square root. Andrea and Liam both get 2.8 meters per second. We'll just give everybody a few seconds here to potentially catch up and see if they agree. Evan agrees. Okay. I want to, well, we'll do number 2, and then maybe I'll show you the video here. This is, somebody actually, it's called Hot Wheels X Games. Somebody actually, Hot Wheels are little tiny miniature cars, if you don't know what they are. And you buy little plastic lengths of track that you put together, and you can make what's called a loop-to-loop. And this is a life-size loop-to-loop. And I apologize because when I photocopied this, the image did not come out very well on your handout. But you can see, it's not even that great here because this is a capture. You can see down at the bottom a car. The car is, I'll just highlight it, this is the car here. And it's not on the track right now, but the idea is, oh yeah, it is on the track. The idea is it's going to go through and come down the other side. And there's 2 loops here, and they send 2 cars through at the same time. What we're asked to do is estimate how fast the car must be traveling when it gets to the top to stay on track. So I'm going to estimate the length of that car to be, I'll say 7 feet. Typical kind of length of that type of a car. And I guess what I'm interested in is if that is Am I back? Okay. My battery in my mic pack died on me. So what I was saying was that this distance here is 7 feet, and I've reproduced it here. That's 1, 2, 3, 4. It's about 5 car lengths for the diameter of this. So if I take 5 times 7, we're looking at about 30 to 35 feet in. We've got about 35 feet for a diameter. This is just an approximation. There are 3 feet in a meter. So if I take 35 feet and I divide by 3, we've got a diameter of about 11.7 meters. If I divide that by 2, we've got a radius of about 5.8 meters. This is just an estimation. Okay, that's the radius. Let's call it 6 meters. So how are we going to find the minimum speed? We're going to say that the centripetal force, which is the net force, is only going to be provided by the force due to gravity acting on the car. So this is ma, which is mv squared over r. I mean, we just did this calculation in the previous question. This is mg. The m's cancel, and I'm left with v equals the square root of rg. I don't know if, while you're doing that calculation, I'll just keep talking. I don't know if you heard me, but I will show you maybe a little bit later today, but definitely tomorrow, the video of this. There's also a link that you can go to. The video is quite long, and the actual action happens in about the last minute. So what do we get here? We get the radius, which I said was 6 meters. It's just an estimation, times 9.81, and we have to take the square root. So the car, when it gets to the top, has to be traveling at about 6.7 meters per second, or sorry, 7.7. You need to understand something. Let's turn that to kilometers per hour. If the car is traveling, that doesn't seem very fast, does it? It's not. 28 kilometers per hour? But I'll tell you what, if you're in that car and you enter the bottom of the curve at 28 kilometers per hour, you are not going to make it. Because as you climb, and if you've ever driven on a hill, you know this, as you climb up a hill, your car slows down. We would never worry about trying to find the speed that they need to enter at the bottom at in this unit. So I'm going to end it there. If you take a quick look at number 3, we could do number 3, but I'm not going to. I'm just going to remind you what I told you, which is that this is the applied force. There's no string, it's just the applied force. So anytime you're doing any of these problems from today's lesson dealing with vertical circular motion, if you are asked about weight, apparent weight, it's the applied force. It's the same as it was with vertical motion in a line. So I really try not to make this happen, that we go almost right to the end of the 2 hours, but we have to be flexible here, everybody. We go from having, 2 hours and 40 minutes roughly of class time when we were in the building to 2 hours. Something's got to give from time to time. And over the past week, what's given on certain days is we haven't done 2 lessons. Sometimes we're going to have to do 2 lessons and it will cut into the class time. You have some questions to work on dealing with everything we talked about in this lesson and in the previous lesson.